Welcome to Hess's law. So, because enthalpy is a state function, this means that the change in enthalpy going from some initial state to a final state does not depend on the pathway. And this means that in going from reactants to products, that change in enthalpy is the same regardless of whether the change is performed in one step or a series of steps. And this is called Hess's law. So, let's look at the oxidation of nitrogen with oxygen. So we have N2 plus O2 gives us NO2, nitrogen dioxide. So we have here a change in enthalpy, and here I'm labeling this delta H1 because we're going to have some additional delta H's later on, some additional change in enthalpies. So that enthalpy change is 68 kilojoules. So we could carry out this reaction in two separate steps instead of one. So with one step, we got delta H1 of 68 kilojoules. If, on the other hand, we first react a nitrogen molecule N2 with one oxygen molecule to give us two NO molecules, that has an enthalpy change of 180 kilojoules, positive value. And then if we take those two NO molecules and react those with another oxygen molecule, that gives us two NO2. And that gives us an enthalpy change of negative 112 kilojoules. Now, you may notice that if we add 180 kilojoules and negative 112 kilojoules, we get 68 kilojoules. And this is what Hess's law says, is that from the enthalpy change perspective, we started out here, we ended up there. We did that in both cases, right? Here we started out with N2 plus O2, and we added another O2 later, so we have N2 plus O2. The overall reaction here is the same as this reaction. That means that the overall enthalpy change for these two steps has to be the same as the enthalpy change for that single step by itself, if it were all to occur at once. So again, the sum of our two steps given above gives the overall reaction, and the sum of the enthalpy changes for the two steps gives the overall enthalpy change. So we have delta H1 is equal to delta H2 plus delta H3. So 68 kilojoules is equal to 180 kilojoules plus this negative 112 kilojoules. And we can show that graphically by saying, well, we start out here with N2 and two O2 molecules, and we can move up in one step to two NO2 molecules, and that enthalpy change is 68 kilojoules. Or we could do this in two steps. We could react with one oxygen molecule first and end up with, we could go from an N2 molecule and two O2 molecules to one O2 molecule and two NO molecules. And then from there, same place, we move down to two NO2 molecules, so we combine that second oxygen molecule. And we're going up by 180 kilojoules, then we come down by 112. Well, up by 180, down by 112 is the same as up by 68. So overall, we get our overall enthalpy change, 68 kilojoules. So it's important to note a few characteristics of enthalpy changes. If a reaction is reversed, then that means that the sign of delta H is reversed. So if delta H was positive, it becomes negative. If it was negative, it becomes positive. The magnitude of delta H is directly proportional to the quantities of reactants and products in a reaction, which means that the coefficients in a balanced reaction are multiplied by an integer, then the value of delta H is multiplied by that same integer. So essentially, we can now talk about this delta H as a value per gram or per mole of reactant. So this was Hess's law.